So we were having swordfish at dinner last night. My brother is an expert at knowing exactly where to go off the coast of Florida.
Danny, what are you...
Huh? Supposed to say swordfish?
Yeah, I did. We're talking about swordfish.
And we're talking about how scientists use Euler's constant to guess their age based on the certain characteristics of their bodies, length and width, such things like that. Okay, Goofy. You go to your office? Alright, baby girl. Let's go. Anyways, my brother is really good at swordfish, and so we eat a lot of fresh swordfish. While we were eating last night, I was wondering if he knows about how long they live. And so his wife actually looked it up, Googled it, and found a scientific paper, and she read that they live almost up to 16 years, which is kind of like eons in the life of fish. But she handed me the phone because it was a scientific research paper, and she saw some equations. So I'm going to show you what they were real quick. L sub t is equal to L sub infinity times 1 minus e to the negative k times the age of the fish. So that's t minus t sub naught. And this is called the von Bertalanffy equation. Bertalanffy equation. Okay. Where L sub infinity is the maximum possible length, probably limited by the longest swordfish ever found. And E is the star of the show tonight. That is Euler's constant. And okay, so K is just an empirical, or it's an empirical constant that is arrived at. It's kind of the best number that fits in this equation to make it so that this number fits the actual experimentally observed data. So if we just draw this really quickly, let's see. So if we look at this swordfish, the orbital length is from the eyeball, the orbital cavity, or whatever. It's a anatomical term. So this is called the orbital length. This can be determined very near with high accuracy by this equation. This is the current age minus the initial age, so it's just the current age. K is a constant that is determined experimentally so that this equation fits the data. And this is the longest observed length, so it's the kind of the limiting factor. This inside here, because it's E, it's a positive number, so this is 2.71. Anything to the negative exponent is going to be any positive number to the negative exponent will always turn into a fraction with a value between 0 and 1. So that means this whole value will be less than 1. And that means that multiplying anything between 0 and 1, less than 1, times a number will always give you a number less than the number you're multiplying it with. So, the point of all that is that it's really, really interesting that this constant that Bernoulli initially discovered, but Euler popularized and applied widely, is the only mathematical concept other than, multiplying things in the exponent, which adding variables in the exponent, which is kind of hand in hand with using this constant. It's really the only complex thing about this equation. So, just to put it in practical terms, that means that this number is experimentally known, so it's a constant, never changes. This number is Euler's constant, and this number is also experimental constant. We know that. So you have two unknowns. If you know the age of the fish, you're going to know this orbital length. You're going to know this before you know the age. So what that means is that once we know the length, if you go out, happen to catch a swordfish, which is highly unlikely if you're not specifically targeting swordfish. If you do though, you pull one in, you want to know how old the fella is. What you're going to do is measure this, and then Google what these three constants are, and some quick math will allow you to solve for its age. just looked it up. Looks like K is 0.25. So and then we have T. And then 1 minus the ratio of our fish versus the experimental or theoretical maximum length, which, interestingly for females, looks like it's 220, which is longer than the 193 centimeters that males are. So we'll do the max length is 220. We'll pretend we got a big one. So we'll do 210 over 220. So I got the calculator out. We're going to do 1 minus 21 divided by 22, because that's the same as, I didn't do minus. That's the same as 210 divided by 220. We'll pretend it doesn't repeat. And now what you do is take the natural log of both sides, which means that e to this power is 0.0455. So we need to figure out what all this means. Basically, is that the answer basically means that what age would make it so that e to the power of -1/4 of that age gives us the ratio 1/22. What this reduces to is -2t equals this value. So we got ln of our answer, and that gives us -3.091. And then that means t is the ratio of -3.091 to -0.25. And the negatives cancel, so 12.36 years old. And we'll just do a roughly equals 12.36 years old. So that's just one of the many, many examples of how Euler's constant is used in, oh man, everything from radioactive decay to bacteria cultures to other biological growth patterns to economics. So I just wanted to open with this, even though it took a long, long time to figure out. We were studying a mathematician who was prolific but also extremely profound in his understanding of the universe in the way that he could apply his mathematics to real world situations, which I don't always know if that is always the case. I don't know if that's true for many mathematicians. There's perhaps many very abstract, complex processes, such as the famous Riemann vectors that Einstein ended up relying upon heavily, fundamentally, to verify his equations of relativity. But they weren't seemingly practically useful until he was able to use them and apply them to the real world. So that's a interesting feature of mathematics that sometimes, and perhaps ultimately all of the time for logically tight mathematics, but at least some of the time. It wasn't Riemann vectors, it was a Riemann tensors, which is a mathematical interpretation of the curvature of non-Euclidean space. So that's a space that fundamentally doesn't follow the rules that Euclid laid out 2,000 plus years ago. So, in effect, we as humans didn't realize that there could be a practical application of such an abstract concept as non-flat space. Space in which two perfectly parallel lines intersected. Because in Euclidean space, parallel lines will never intersect. In non-Euclidean space, we have the concept of space as curving. And the analogy that's often used rather, it's the curved Earth. If you're at the North Pole and you go in a straight line, so looking from overhead, for instance, if you went this way from the North Pole and then you turned exactly 90 degrees and you started walking that way, you would also reach the equator. And that just means that what's interesting about this is that it's 90 degrees here. You go down and you're at 90 degrees relative to the equator, or the line intersecting both these 2 points. Ultimately, you form a triangle with 3 seemingly straight lines, 3 90-degree angles connecting them. The non-Euclidean analogy would be that if this was the equator and you're at 2 different spots and you go straight north, these 2 lines in flat space, if the Earth was not curved, would never intersect. But because the Earth is curved, and remember this is an analogy, they do connect and they intersect. So this means that it's a different way. It means that now we had, with this revolutionary mathematics, it gave us a really powerful tool with which to analyze observations. If we're on a planet, so if we're on Earth and we're looking at a star behind, right near the sun, say we're looking at this one, the light that we see in standard Euclidean geometry that we learn using the Pythagorean theorem doesn't actually follow that path. So what we think we're seeing, in other words, where we think the star is wrong based on Euclidean geometry. We need non-Euclidean Einsteinian geometry, that the actual star we're seeing is, in fact, a distance over here. And this is exaggerated, but it was proven in 1919 with a solar eclipse that Einstein's equations correctly predicted where a certain star would be as it neared the sun's corona relative to the Earth. And the Euclidean Newtonian equations actually did not. It was inaccurate. So this actual was the observed position, and after applying Einstein's equations, we realized this was the actual position of the stars. Getting to the main, the point of this video is that, Euler worked in a ridiculous number of areas in mathematics and physics, in engineering and also music. So no doubt he, if he had lived 100 years later, he would have been at the forefront of non-Euclidean geometry, and maybe he was, and I just didn't realize it in my little research. It helps give an understanding in a context in which to put all these mathematical discoveries I'm about to talk about in. Some of math isn't verified in the real world until much, much later, after it's discovered or created, if you will. So, Euler worked in geometry, infinitesimal calculus, trigonometry, algebra, number theory, as well as multiple areas of physics. He's the only mathematician to have not one, but two numbers named after him. You have Euler's number, which is called E, approximately equal to 2.718. And then we have the Euler-Mascheroni constant, which is referenced as gamma, the Greek letter gamma, is approximately equal to 0.57721. I'm not going to do him justice here, but I will talk about at least a handful of discoveries that he made. For one, he introduced and popularized several notational conventions and concepts that we all know today. Perhaps the most familiar, he introduced the concept of a function, the infamous f of x. The infamous f of x that we all just want to write as y. We, from 6th to 7th grade, probably earlier in other countries, we switch from y equals to f of x equals, and we wonder why we have to switch from one simple letter we know represents a number to a weird multi-letter parentheses thing. But ironically, it's meant for clarity. So it's trying to look at this as a unit and saying this is a function that depends on what x is, because m and b are traditionally just numbers that we already know the value of, whereas x is meant to represent a constantly changing, I shouldn't use constant there, a set of numbers. So this means really a function of x, which means that whatever the value is over here is a function or is dependent on what x is. And so we say the length of the orbital length of a swordfish is a function of the age of it. The length doesn't determine the age, but the age has some causal or determining effect on its length. So Euler was one of the main guys to, unfortunately for you middle schoolers out there, introduce and popularize that concept. So on top of this, he also popularized the notation for trigonometry, for sine and cosine as sine of x and cosine of x, sine of x and cosine of x. So, it's not to mention e and the natural logarithm of e that we've already talked about. And logarithms are for another episode, but a logarithm is just a inverse of the exponent, natural logarithm. Okay. He made use of the Greek letter sigma for summations. And we're going to ring up our friend Decaf-Math in a little bit to help us understand one of Euler's famous identities. So you'll get to see what this means in a little bit. But for now we know it means sigma, and it just represents summations of functions. He used, let's see, the letter I to represent square root of -1, or the imaginary number, also known as complex numbers. He introduced pi to a popular audience, being roughly equal to 3.14159, meaning for any circle, any perfect circle, it's the circumference divided by its diameter. It's always going to equal 3.14. Of course, that's pi. He didn't create that notation, but he did popularize it. So even if you, well, actually, especially if you stopped taking math in high school, the bulk of the terminology and symbols that you're familiar with has, you can thank Euler for that. And believe it or not, he genuinely made it much more clear and distinct and easy to manipulate such symbols. So, that's just the tip of the iceberg, though. Something you STEM majors, taking an upper level mathematics, might recognize from your shortcuts to solving differential equations is Euler's famous formula, which of course he also created. Let's just make a nice. So with this formula, what he did was play with the exponential function so that it could relate to not only complex numbers, I, square root of -1, but also trigonometric symbols, the famous sine and cosine functions, and threw in, A equals B and B equals C type of syllogism. So therefore, we love this therefore symbol in math. Therefore, A equals C. So he made this famous formula where e to the power of I, square root of -1, times an angle can also be rewritten in the form of trigonometric equations. Let's see, what is it? Cosine of phi times plus I sine of phi plus I sine of phi. Thus he combined sines and cosines with the mysterious imaginary numbers and transcendental number e. So without this function to convert from polar to Cartesian coordinate systems, Cartesian being the famous XY coordinate system that you draw lines on, and you have little XY coordinates. To a polar system that instead of X and Y axes, they change that into a length R and an angle phi. And it's an easy way to convert. So without this simple, seemingly innocuous conversion. I looked it up. You wouldn't be able to. We wouldn't have electronics, rockets, stuff like your AC thermostat. We wouldn't understand how these things worked, and therefore we wouldn't have been able to have engineered and created them. I mean, radiation therapy, modern chemistry even, these might still be waiting to be discovered. So you're probably starting to think like, alright, this is cool and all, and that's good that you can use that, but isn't there an easier way to understand why it's important? Well, at this point I'm really happy. We know a gal. I wonder if she'd be around. I wonder if I could call up Decaf-Math to help us out, to help us understand this. Because there's a special case, I think, of this called Euler's identity. Euler's. Let's fix that. Okay. And this looks like this. E to the I pi. So now it's got pi in there. Equals. Oh no, sorry. Plus 1 plus the number 1 equals 0. And this caught my attention because it was called the most remarkable formula in mathematics by this guy right here, Richard Feynman, a famous genius and quirky physicist, renowned for his own breakthroughs in quantum electrodynamics. The notions of addition, multiplication, exponentiation, inequality, and the fact that these are used with 5 of the most fundamental yet mysterious constants in all of mathematics. So it's I don't know, to me that was just a really interesting observation. So I'd be curious to know exactly how Euler was able to conjure up, how the heck did he cram so many fancy constants into one simple equation? So, you know what, let me go ahead and call Decaf up. We'll see if she can enlighten us a little bit as to how Euler came up with this brilliant equation.
Hello? Oh, hi, Rich. Yeah, I'd love to help. Euler's formula, huh? Yeah, let's see if we can prove it. I was actually just taking a look at it. Alright, I'll see ya. Bye. So let's take a look at this beautiful, beautiful equation. E to the I pi plus 1 equals 0. So simple, yet so complex, huh? So one thing I'm going to start with is I'm going to move this plus 1 over to the other side, just using a little bit of algebra. So e to the I pi then equals negative 1. 0 minus 1 is negative 1, right? So we get e to the I pi equals negative 1. And the reason I wanted to do that is because I'll realize that that is a special case of this formula, e to the ix equals cosine x plus I sine x. I see here that I have e to the ix and then I have e to the I pi, which kind of hints at the fact that maybe if I plug in pi in place of x, I can get something. So if I plug in pi for x in this entire equation, let's see what we get. We get e to the I pi equals cosine pi plus I sine pi. If you've never learned it, don't worry, I'll just do all the math today. But cosine pi is -1. It is the x-coordinate, because it's cosine, the x-coordinate of the point that corresponds to the angle pi, which is half our circle, right? So -1, and then sine pi is actually 0, because it's the y-coordinate, so 0 times I is still going to be 0, and -1 plus 0 is -1. So e to the I pi equals -1. Okay, cool. So this isn't really a proof, it's just an observation that our formula, our very seemingly simple formula, is actually a special case of this thing. So knowing that, now our goal will be to simply prove this thing. Simply prove. So there are many ways to actually prove this. So today I'm just going to go over two of my favorite, because I think they're kind of cute and fun. They both rely heavily on calculus and calculus concepts. So I kind of feel like this is where I'm going to lose people, or people who are really interested or love calculus might find this fascinating. But either way, I hope that this is relaxing and fun. So I wrote out the Taylor series already, so this is the first way. I'm going to expand this, and this. And so e to the I x, cosine x, and sine x. And with Taylor series, you can basically just expand a function into like around a point. So the Taylor series about a point is f of x is f of a. So f of the value of the function at the point a plus f prime of a times x minus a, and those two terms make the linear approximation, but you can keep going. So plus the second derivative at a times x minus a squared over 2 factorial plus ... to infinity. And so that's how you expand a function. And specifically, if you set a equals 0, you get the Maclaurin series. So, and I already wrote the Maclaurin series for e to the x, cosine x, and sine x, and sort of intuitively, we're just plugging in each of these functions into this thing at a equals 0. So intuitively, e to the x, we know that the derivative of u to the x is e to the x, and so the second derivative is e to the x, and it's always going to be e to the x. But then at a equals 0, so e to the a, so e to the 0 is 1. So all of these coefficients are going to be 1, and then everything else goes away. So x squared over 2 factorial, x cubed over 3 factorial, ... And for cosine and sine, it's actually not too bad. It's actually really cool, because if you remember the derivatives of these trig functions, for instance, cosine x, the derivative of cosine x is negative sine x, the derivative of negative sine x is negative cosine x, the derivative of negative cosine x is sine x, and the derivative of sine x is back to cosine x. So it's cyclical. So if you plug in a equals 0 into those, or x equals 0 into those, you can notice that all of the sine terms are going to go away, because sine 0 is 0, and negative sine 0 is 0 still. So you're left with like this every other pattern, and cosine of 0 is 1, and negative cosine of 0 is going to be -1. So you get this negative, positive, negative with every other term. So that's why it's all the even And so sine x has the same cyclical pattern for the derivatives, but it's the opposite of the cosine, where you're doing the odd parts. So with that, I'm just going to start with this e to the x. I'm going to start on one side. So I have e to the ix, but I'm actually going to start by writing out the one for e to the x. So I'm just copying this part. And then what I'm going to do is put in, instead of x, so anywhere I have x here, I'm going to put ix. I could have just written like e to the y, or not y because that's going to be confusing with f of x, but you know, e to the something. So if you imagine that every time I have an x here, since I have e to the ix, I'm just going to put in ix instead, okay? So e to the ix equal, and now I just have to expand all of these exponents here because I have ix squared. So I'm going to expand that just using our rules for exponents. So ix squared is I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus dot dot dot. And we actually recently talked about the cycles of these exponents in our last Hangout session, so feel free to check that out and kind of review. But we have one, so I'm just gonna simplify the I squared and the I cubed parts, and the pattern goes 1, I, -1, because I squared is -1, and then I cubed would be that -1 times another I, so -I, and then 1, and then back to I. So it's every 4. So you have 1 plus ix, and then a plus x to the 4th over 4 factorial. So I'm just going to do, just one extra term so you can see somewhat of a pattern. And so that's great and all, but who cares, right? So actually, if we notice which terms have i's and which terms don't, if we group this, we'll actually see that we'll have a real part and an imaginary part. So let's see what we have here. And so I'm just going to group those together and just move them because I can, because addition is commutative, so we can just regroup. So we have 1 minus x squared over 2 factorial plus 6 over 6 factorial. I think you get the point. Dot, dot, dot. I'm going to put a parenthesis around that to group those together. And then for the I terms, I'm going to group those together, but I'm just going to go ahead and factor out an I. Just plus, and then I, and then, so I'm going to factor out that I, and then I get x minus dot, dot, dot. And do we see where we're going with this? This is so cool. This 1 minus x squared over 2 factorial blah 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 is actually the expansion for cosine x. So basically, this is cosine x. So I'm just going to write over myself here, but cosine x. And this, we still have our I, but this inside part is sine x, so plus I sine x. So we have cosine x plus I sine x. Ta-da! Okay, so another really cute way to do it is also based on calculus, but not quite so complex. If we let f of x equals e to the negative I x times cosine x plus I sine x for all x in the real numbers, okay? So this might seem kind of arbitrary, you can kind of see this mimicking this, but why we do this is because if we take the derivative, the first derivative, you get 0. So the first part and the second part of the product will actually cancel, to give you 0. And why that's significant is if the derivative is always 0, then you know that f is a constant. It's the same everywhere, so I can pick any arbitrary point. So conveniently, I am going to pick x equals 0 and see what we get. So f of 0 is, if I just plug in 0 for all the x's, I get e to the negative I times 0, so e to the 0 times cos 0 plus I sine 0, and e to the 0 is 1, cosine 0 is 1, sine 0 is 0, times I is still 0, so 1 times 1 is 1. So f of 0 is 1, which from our derivative here we see that f of x equals 1 always, everywhere. Which means that since we picked f of x like this, e to the negative I x times this stuff, I sine x equals 1. Algebraically, if I move this first part over here, I get 1 over e to the negative ix, which is e to the positive ix. And we don't have to worry about dividing by 0 because e to the stuff is never going to be 0. So we get e to the ix. So e to the I, like the positive ix. Isn't that cute? I like this one too, it's really cute. So that just comes from, recognizing that the derivative of this, that's really cool. But you have to kind of be clever in setting what your f of x is. And I'm not sure that I would be able to just do that derivative in my head and realize, oh wow, it's 0, because you have to do the product rule, you have to do the chain rule. So that's kind of a mess. But still, very cute. Okay, so I hope that was helpful. I hope this was fun. It was definitely fun for me. And I will see you around soon. Say hello to Molly and the manager for me. And I'm sending you all my love. Take care. And if you ever need some math help, just give me a ring and I will see you around. Bye.
Wow, that's really cool, Decaf. I appreciate that. Thanks for taking your time to explain all that to us. I never really realized there's so many different angles from which you can view formulas like that. So it looks like looks like this thing is the focal point of a lot of modern mathematics. A lot of maths that really help us describe nature. I know the McLaren and the Taylor series, that these are variations of power series that many engineers and physicists use to make predictions about a lot of electromagnetic phenomena. That's really cool. I appreciate that. Thanks for helping us out. So, from what else I've read, Euler didn't stop there. In 1988, the Mathematical Intelligencer voted that the most beautiful mathematical formula ever. But that was just Euler getting started. He pioneered and had a hand in so many higher mathematical concepts. Just a few are in the areas of higher transcendental functions, with his introduction of the gamma function, which I'm sure incorporated this. He delved into integration with complex limits, which is a form of calculus integration. I guess it's a prototype of a field called modern complex analysis. And he did calculus of variations with the Euler-Lagrange equations. Always like writing my L's like that. He single-handedly introduced a new field of study, analytic number theory too, by fusing disparate branches of maths, and in the process created the theory of hypergeometric series, as well as the Q-series, hyperbolic trigonometric functions, and the analytical theory of continued fractions. Can you tell I have no idea what I'm talking about? This guy was clearly the Elon Musk of mathematics, pushing the boundaries of what we thought possible. But no, Euler didn't stop there. He made enduring contributions to the fields of number theory, graph theory, applied mathematics, physics, astronomy, logic, and even music. So much of this is from his Wikipedia page, if you guys are interested in delving a little deeper. But I broke off those into number theory, graph theory, physics, astronomy, logic, and music, different sections that I'll briefly talk about. So in number theory, he developed some of Pierre de Fermat's, not his last theorem, but some of his ideas, and disproved some of his less famous conjectures. He contributed significantly to the theory of perfect numbers, which had fascinated mathematicians all the way back since Euclid. Speaking of Euclidean geometry. And this was an interesting little side note. I'll try not to take too long on, but I was curious what a perfect number even was. And I guess what it is, it's a positive integer that is equal to the sum of its proper positive divisors. And what that means is that if you take a number, let's do a simple number like 6, for example. 6 can be broken up. Let's see. Its factors are 1, 2, 3, and itself. So other than itself, a perfect number adds up, or its divisors add up to itself. And that's true. 6 is the first perfect number. This definition is ancient though, so it's not specific to Euler. It appeared as early as Euclid's Elements, where it's called the, let's see if I can write this down. It's called the Telos. So what this means is the perfect, ideal, or complete number. Even weirder is that Euclid also proved a formulation rule, where he had a formula that that worked for that worked to give even perfect numbers. So, for instance, let's see, his formula was Q times Q, the same number, plus 1, all that divided by 2. So that's always going to be an even perfect number if Q is what's called a Mersenne prime. So a Mersenne prime is a number, it's a prime number that's equivalent to 2 to the power of another prime number minus 1. Let me rewrite that. If Q is a Mersenne prime, where a Mersenne prime one less than 2 to the power of another prime number. So, 2 to the power of another prime number minus 1. It's a Mersenne prime. If you use a Mersenne prime in this formula that Euclid, thousands of years ago, discovered, it's going to pop out perfect numbers whose divisors other than itself add up to itself. And this is one of those weird examples of consistency in mathematics that we don't necessarily see in nature yet. But who knows? Like Riemann tensors, a genius like Einstein may come along one day and use this to revolutionize our understanding of the physical, maybe mental, maybe they're one and the same world. So, as an example, 7 is a Mersenne prime. And when we plug 7 into this, we get 6. So we can show that 7 can be derived from this formula. If we do, instead of this, we do 2 to the power of, let's use the prime number 3. Well, 2 to the power 3 is 8, minus 1 is indeed 7. Nothing really spectacular there. Let's see. If we were to make our prime number 5 at p equals 3, we get this. At p equals 5, we're going to get 2 to the power of 5 is 31, and that is a Mersenne prime. So if we go ahead and call 31Q in this formula up here, what we're going to do is, after a little bit of tedious adding up, factoring and then adding up, which I'll do for you, is so we have 31 times 32 divided by that quantity divided by 2 is 992. Divided by 2 is 496. Now, I already plugged this into Google. Maybe Wolfram Alpha, I forget. But the factors of 496 are 280, 248, 124, and 4. And then 62 and 8. And 31 and 16. So, other than the number itself, if we add up to 48, 124, 4, 8, and 62, 16, and 31, what do we get? Is, let's see, we got plus 248 plus 24 plus 4, 62. That one sticks. And 16 and 31. I get 495. So I must have forgot one, and I did. You can't leave out one. That's the key. That's the key right there. And so that's everything that was done by Euclid 2,000 years later, about almost 300 years ago. So what Euler did on top of this is all what Euclid had already proved. Euler proved that all even perfect numbers are related to Mersenne primes by multiplying a Mersenne prime by a number of 1 less power than the prime exponent that created the Mersenne prime. So written simply, every even perfect number can be found by this equation. Is given by 2 to the power of n minus 1 times 2 to the power of n, that quantity, minus 1, where 2 to the power of n minus 1 is, of course, a Mersenne prime. And n is a prime. Number. So there's a theorem that of course goes along with it to prove it mathematically. And this theorem is known as the the Euclid Euler. There. And of course, if throughout this video I happen to slip up and call him Euler, please forgive me. You can imagine why. But in 1772, Euler had proved that 2 to the power of 31 minus 1 is 2,147,647. It's a Mersenne prime. And if this was a Mersenne prime, and we plugged it into this formula, we would get the even perfect number of 2.30584301. I'm going to use scientific notation here because it's such a large number. Times 10 to the 18th times 10 to the 18th. The Mersenne, this one remained the largest known prime for 100 years, roughly, until about 1867. So that's just one of Euler's many contributions to number theory. If we move on to graph theory, and I forget who it was, one of you very coincidentally had asked about the graph theory. And so here we are. So Euler came up with a solution to what's called the 7 bridges of Königsberg problem. And it's considered to be the first theorem of graph theory. In 1735, he presented the solution to the problem of, if we have a river with an island in the middle of it, with 7 total bridges connecting it, can you go over each bridge once and only once? Boom, boom. So roughly it looks like this. You have a river, an island, going over there, there, and like that. And then you have one bridge there, one bridge there. So you got 5 total bridges connecting the island, and then 2 more additional bridges connecting the mainland across the river at a downstream point. Now what modern graph theorists are able to do, and this is a useful way to get your feet wet in, well, graph theory, but also for it applies in electronics as well. If you're looking at circuits that, especially if you have loose wires that aren't simply on a 2-dimensional printed circuit board, it's easy sometimes to get confused as to what the problem might look like. So a way to greatly simplify it is to make a graph. And one useful graph is to look at the nodes this problem, and we consider the nodes, the points to which the bridges or the paths lead, and the points which they have in common. And this is probably some sort of relative IQ test type question with topology. You notice that, you might be able to notice, this land connects these three nodes. So we represent that with this node, or this dot, right here. And similarly, this node has 1, 2, 3, 4, 5 bridges connecting to it. So we represent that with this node right here. Over here we have 3. And down here would be this area of land. So let's see, this node connects 1, 2, 3. These two bridges connect to the middle. Let's make these more prominent. And then this node over here is connected by the middle, the upper, and the bottom. So we have and then likewise this middle is connected to the bottom by 2, which is also connected to the right hand bit of the mainland. Or I guess it's a second island. I'm not sure if the river ever connects again. Be represented like that. So the whole point of the problem was to show that logistically you can't pick any path that will lead you over one bridge only once and return to your starting point. So we can try it. 1, 2, 3, 4, 5. And now we went across this bridge, this, and this, but we didn't go across 3 of these. So if I switch colors, so that would look like this. 1, 2, 3, and then 4. So I didn't go this, and this bridge. So if I switch colors, we can try, let's see, 1, 2, 3, 4, and now I can either go here and return to my starting point, missing this bridge, or I go here, but from there I would have to double up on this one bridge to return to my starting point, and that would look like this. 1, 2, 3, and then 4. This pen doesn't like working. And then here I would have to either go here and not go on that bridge, or if I did, I would end up here, and I've already went over 4 of the 5 bridges, so I would be backtracking. So you can try this multiple ways, but of course a mathematical proof is much more than just trial and error. I don't have the wherewithal, I don't have the knowledge or skills, maybe, to show you the proof. But Euler certainly did, and he essentially founded what's called graph theory with his logical refutation of this problem, proving that there's no such thing as a Eulerian circuit. So this is, of course, his namesake right here. Next, Euler got into physics and astronomy. He was studying Uranus right before he died. And he was actually studying and discussing the properties of the newly found planet Uranus on the day that he died from a brain aneurysm. Euler helped develop the Euler-Bernoulli beam equation, which any of you mechanical or civil engineers would be familiar with. It became a cornerstone of engineering, and without it, many of the more complex structures, especially skyscrapers and bridges, would be much more difficult to build, I'm sure. So, Euler, aside from applying successfully, mind you, many of his analytic tools to problems in classical mechanics, he also applied these techniques to celestial problems. And mind you, he was nearly blind, so there's a paper I looked up that literally was titled Euler the Blind Astronomer and Mathematician, which is a pretty bold occupation to be a key figure in when it relies so heavily upon seeing and eyesight. So his astronomy, his work in astronomy, he applied some of his mathematics to celestial bodies and orbits, of course. His accomplishments include determining with great accuracy the orbits of the planets. The orbits of the planets. With his he published in 1735, by the way, the same year that he worked out the 7 bridges of Königsberg solution. I can't even describe how prolific he really was. But he published in this year a work on the motions of the planets. And in this problem, in this work, he established a crucial element of not only modern astronomy, but also an equation of great importance in astronautics to help determine the position of artificial satellites and space probes. at every single point in their trajectories. So he expanded on the works of Kepler and Newton, even defining, or deriving rather, some of Kepler's famous equations iteratively from or in other words, in a different manner than Kepler did. One of his equations was to find the orbit in polar coordinates. So here it would be like R equals P plus E cosine phi, which equals A times 1 minus E squared over 1 plus E cosine B prime, where E here doesn't mean his number, but it's the eccentricity of the orbit, which means how much it deviates from a circle. It's how elliptic it is. V is the true anomaly angle. A is the semi-major axis. True anomaly angle, semi-major axis. P is the semi-lattice rectum. You guys might know that from Algebra 2, doing conic sections. Okay. So, anyways, Euler was just so prolific. His equations were riding on the tailcoats of Newton's very recently in his time established, confirmed equations that ridiculously helped sailors and voyagers, adventurers, expeditioners, merchants, and anybody voyaging across large expanses of the ocean. So Euler was one of the key figures in helping explorers travel by the stars in a very, very accurate way, because even minor deviations, small inaccuracies, if the theory was wrong, would lead to huge errors. And if you're looking for a little mile-long island in the vast thousands of miles wide, long Pacific Ocean, you're going to miss it even by 30 miles. Maybe 30 miles would have been within the sights of some of the better telescopes on board, but nonetheless, it was crucial for, sailors depended on these equations, being able to navigate by the stars. And when you're on the Earth, looking up into the stars, the night sky, it really helps to know the position of where the other planets are supposed to be relative to the background stars, because then you know exactly where on Earth you are. So, anyways, he was huge in the field of engineering, navigation, astronomical, anything that uses the stars. So in addition, Euler made important contributions in optics as well. he disagreed with Newton's corpuscular theory of light in the optics, which was when the prevailing, which at that time was the prevailing theory. His 1740s paper on optics helped ensure that the wave light theory of light, wave theory of light, so it was that was really what became dominant, at least until the development of the early 20th century quantum theory of light. In 1757, he published an important set of equations for an viscid flow, now known as the Euler equations, naturally enough. In a viscid flow, there's a little contraption that's like this. So there's a container that's hanging, not touching anything, and it's filled with fluid. And so he hadn't observed it. This is another example of extrapolation in mathematics. Eventually being able to correlate and define, well, not define, but describe very accurately a real-world phenomenon. And this is of what's called inviscid flow. Man, there's something really satisfying about drawing concentric circles. I don't know why. Anyways, so inviscid flow is a flow. It's an adjective you can apply to a fluid that has zero viscosity, which means resistance of itself to, really resistance of itself to begin motion, which means resistance to motion, really. Just think of the exact opposite of a cold, thick maple syrup. And this is fluid that if placed in a glass container, something with, relatively smooth features, it will actually climb up against gravity and drop down outside of it. So this is, it's really crazy. It's just a fluid that essentially can defy gravity and climb out of a container that it's in. And so that's why I drew this, showing a fluid that's climbing out and dripping down the outside of a container that it's nowhere near filled all the way up inside of. This today is known as a superfluid, but it's something that Euler, again, had intuition about, knowledge of the physical aspects of water that was observable, and he took it to its extreme, its mathematically logical extreme, and said if the amount of viscosity that syrup or water has was eliminated, what would this superfluid look like? And this is what he predicted. And sure enough, his equations are very accurate. The next is just a small but interesting contribution to the field of logic that Euler made. And it's the Venn diagram that we know. So, just like we had. So Euler is credited with using closed curves to represent syllogistic reasoning. And what this means essentially is that in a Venn diagram is actually a variant of what Euler was purported to have invented to illustrate logic and reasoning. So for instance, the Euler Venn diagram for this channel might be, we have a subject, we have a set, a classification of phenomena you call ASMR. Inside that, you have many different types of things, stimuli that produce or trigger ASMR. And what I try to do, and maybe one of them would be pure sounds, like ASMR Zeitgeist is very, very good at doing. And another would be more social, more companionship related creations or content, like GB is really good at doing. Yeah. And if you're really on the fringe, maybe you'll even attempt to infuse some education into your ASMR, which might be what the French whisperer, for instance, is really, really good at. And so we have sounds over here, and we have social over here, and then we also have a little bit of educational right in here. And ideally, if I can pull it off, I'd like to be right in this sweet spot. Illuminati confirmed. But yeah, this is exactly what a Venn diagram is really useful for. So, believe it or not, Euler was one of the originators, if not the originator of it. And then lastly, the last thing I left a nice little spot for is his contribution to music theory. Euler's approach with music, of course, is mainly mathematical. His writings on music are not particularly numerous, a few hundred pages in his total production. Of 30,000 pages. which would be roughly, I guess, about 1/16th, for doing some quick math. Oh no, sorry. Way. That was an order of magnitude off there. So, it's funny. So 6.66, which is about 0.006, or 0.6% of his entire body of work. But nonetheless, he was always preoccupied by music. And who wouldn't be, honestly? For a man trying to understand the laws of the universe, and a religious man at that, you have to imagine that he was captivated by music being something as spiritual and profound and moving and emotionally effective as it is to us all. And this is where I'm way out of my depth, but essentially he tried to formulate a theory of genres of music. He has the major notes, so he starts with this diagram: F, C, G, A, C sharp. He makes a grid, as you can see here. H. I've never heard of H. It's weird. G sharp, etc. And he thinks of genres as possible divisions of the octave using the prime numbers 3 and 5, and describes 18 such genres with a general definition of 2MA, where A is the exponent of the genre. In other words, the sum of the exponents of 3 and 5. And 2M is where M is an indefinite number, small or large, so long as the sounds are perceptible. So he's really having a scientific theory of the octaves in the sense of perceptible patterns of waves, of frequencies that we hear. And yeah, I'm really not understanding this at all, but essentially he says you have your octave, and then you have a third where A is the exponent. You have the notes divided into their thirds and their fifths. And I'm going to leave it there because I'd be lying if I tried to explain any further than that, because that really doesn't even make sense to me. So, but essentially it was some interesting diagram is what really caught my eye about it. So if you are familiar with music theory, maybe you can help us out in the comments. But, yeah, it was some weird diagram that I'm sure really, really makes sense to anybody familiar with music theory, but it was way out of my scope. So, that about does it for Euler. He clearly occupied a depth of knowledge and profundity that we can clearly see from his discoveries in this odd realm we call mathematics. He lived and breathed in an abstract landscape found between the internal, natural world of the human mind, mathematics, and the external, natural world of matter and energy. Yet despite his contribution to the mastery of the material world, or maybe because of his closeness to the limits of the human mind, he was a devout Christian and a believer in biblical inerrancy, who wrote apologetics and argued forcefully against the prominent atheists of his time. He believed the Bible to be inspired, and I have no doubt that he acted out this belief with each tireless day immersed in the living sea of mathematics with its clear medium of logic in numbers. Perhaps he even dared to dive deeper than those that hadn't been stricken with blindness, consequently forgoing the paralysis that shakes those encountering the darkness at the edge of human thought.